So in this lecture, I'm going to review the intermolecular attractions that we need to know for college chemistry, AP chemistry, or general knowledge of science. Why not? So in any case, we have to understand that intermolecular attractions are the attractions between molecules. They're not the attractions um, inside of molecules. They're not the bonds. So as we go forward, we understand that because these are the attractions between molecules, if I have molecules of chlorine, bromide, or iodine, how they attract each other determines whether they're a gas, liquid, or a solid. Obviously, iodine attracts other iodine molecules more than the bromide or chlorine because the iodine, is a gas. So the increasing attractive force between the molecules gives you an idea that iodine would be the solid. Bromide somewhere in between, so it's a liquid, and chlorine and fluorine are a gas. But what are those attractions between the molecules? Well, um, we know that these attractions exist. Before we start naming them, we really have to go back into how the real gases and ideal gases deviate. If you haven't never learned this, we know that real gases really have attractive forces between them. Now we know gases exist because of weak attractive forces. So chlorine is a gas because chlorine molecules don't attract other chlorine molecules. These are the attraction between the molecules. We're not talking about the bonding here. But they have to be weak if they're flying around the container and filling the container, traveling hundreds of miles an hour. So we know that gases are ideal gas laws we talked about, and this is not going into detail of this equation, but we've learned already that gases all have attractions for each other. They will all essentially condense into a liquid, so there are some attractions. Therefore, all gases have some real gas behavior. And because they do so, they actually deviate from our ideal gas laws, which state for a gas to be ideal, one of the postulates were that gases don't attract each other. They're independent particles traveling in straight lines. And although this lecture is not about talking about those deviations, I have to talk about them because I'm talking about the attractive forces between the gases. Now these are some very famous lines here, but if you notice, PV over nRT would have to be the same for all gases. Okay, so you know PV equals nRT, so PV over nRT equals some constant, some value that should stay constant. And if it's an ideal gas, it always stays constant. But as we increase the pressure, it dips down because as you increase the pressure, molecules start attracting each other. So the actual pressure of the molecules is lower than what we'd expect, and it dips down. So because of the attractive forces. And that's with these two basic lines. Now we know that an ideal gas goes straight across, and the lighter gases have less of these effects. Like helium doesn't attract itself as much as nitrogen, methane, or fluorine. That's why it is more ideal than the rest. And again, I talk more about these when we talk about van der Waals equation, but I have to bring up van der Waals equation, which is a way for us to correct for the attractions and also the volume differences that we don't have in the ideal gas law. Now, the only reason I'm bringing it up now is because Johannes van der Waals, I'm skipping that part because I'm not sure how to say it, okay, was the first to come up with an equation to understand there are attractions between gases, and the ideal gas laws that we had at the time would not predict the correct behavior or values because gases actually are not ideal. They actually will attract each other. So he actually came up with these values, like for instance the A value in his equation here, I know it's small, he came up with relative values of how well these gases attract each other. Helium is 0.0341, neon is 0.2, argon, and you can see it goes up as the molecules get bigger. Notice if you have a polar molecule like water, it becomes 5.46. All right, so he came up with these values that we're able to use, and pretty impressive for the early 1800s. Now, again, he was the first to talk about these attractive forces. So again, the word van der Waals force actually comes from all the forces of attractions that he actually identified. Now, people have really used van der Waals to explain things that are nonpolar forces because a lot of these early gases were all nonpolar. So it's kind of stuck for a long period. So people tend to use the word van der Waals force. But it's not the best way to explain attractive forces between lone pairs. I think London dispersion forces are, and we'll talk about them. However, getting back to this idea of attractions, we know that in table H, vapor pressure of 4 liquids, we know that there are 4 different liquids here. They all are evaporating at different rates. They're producing a vapor pressure, which is a force of liquid escaping into the gas phase. And we know that these 4 liquids, some evaporate much better than others, and some resist evaporation. Notice water is way over here with ethanoic acid, the vinegar. All right. Now, why do these liquids evaporate at different rates or have different abilities to evaporate? Well, it's because they have different attractive forces. Okay, there are different attractions between the molecules. Propanol here, or acetone, has a boiling point about 56. Its vapor pressure reaches the atmospheric pressure pushing down at 56. Water is 100. So water has a higher boiling point than propanol because it has stronger attractive forces. It's holding on stronger, so therefore it takes a lot more energy to produce the same vapor pressure as propanol. And of course, the magic vapor pressure upward is the standard pressure if we're talking about normal boiling points, things we've already talked about. So there's some implications here. We talked about 4 liquids. And of course, if you go through my presentation, I show you that these liquids do differ in their rates of evaporation. So when I take these 4 liquids, as I've done already, let's go too far. Okay, so I take these 4 liquids maybe at some point, and I was having a difficult time running. Here we go. So I stretched out those 4 liquids, and you can see that what? The acetone or the propanol vaporized the fastest because it had the weaker of all the attractive forces. And it looks like these other 2 liquids here would actually are going to go next. They're going to evaporate next. But what's happening to them is they're actually beating up on themselves. Yeah, they're attracting each other so well. It appears that they're evaporating, but they're jumping up on each other. This ethanol here, which is the second liquid, I try to do this in order of this table here, is actually evaporating second. And notice it's not beating up. So if I go through this, okay, without it crashing on me, okay, maybe, I will show you what's happening. So as I change my camera angle in this video, you can see the ethanol now is going second, all right, as we predicted, and the water and ethanol would go second and third. It looks like the ethanoic acid or the vinegar is going faster than the water, but again, it's only because it's beating up. It's attracting each other. And to give you that idea, when I give you the close-up view of this, whenever it loads, you can see how well this is beating up on themselves because it has stronger intermolecular attractions. Okay, so the first of the intermolecular attractions we're going to talk about is London dispersion forces. And the reason why it's the first one we talk about is because all, and I'll repeat, all molecules have London dispersion forces. Okay? When we teach this the right way, we don't talk about having one or the other type of attractive force. Really, all they have similar. And since every single element, or I should say a molecule, and some are elemental if they bond with themselves, have a cloud of electrons that surround them. So if I look at the electron cloud model, this could be a 1s and this could be a 2s. We've got electron clouds, a place where electrons exist outside the nucleus. Now, London dispersion forces, or LDFs, okay, represent how these clouds change when they come together. Well, essentially, most compounds who are nonpolar do not have a negative or positive side because the electrons are equally interdispersed. But if they were to come together, what would happen is that this cloud could repel this electron. So as I push these close together, this cloud could repel this electron. And what you have is a nucleus here that's attracting these electrons. So by these coming together and having repulsive forces with the electrons and attractive forces with the nucleus, you make something called momentary dipoles. So because this cloud is able to move and change its shape, and we call that polarizability, we can create these momentary dipoles. Let me pull up an animation I think is pretty good to show that. Although I'm not into this guy talking, but to show that, and I guess I have to get through the animation because he's getting paid for this. Okay, we're going to skip this ad. Now I'm going to go through the animation here. Maybe I passed it. Yeah, no, I didn't. So let's go. Here it is. So it's an instantaneous dipole, and essentially what we're going to do is when these things come together, you're going to see this cloud of electrons change its shape, called polarizability. All right, and that changing of its shape with electrons, here we go, jumping to one side or another, creates an uneven distribution of electrons. So right now even, but as they come together, you can see this nucleus is attracting these electrons, and these electrons are repelling the others. And you just created a place where there's a positive side and a negative side for both. So we've got the attraction for the nucleus in one that attracts, and then we have some repulsive forces of the electrons. And that creates these polarizable momentary dipoles that only work when these guys come close. It's a temporary dipole, because once this moves away, they turn off again. So this little tiny positive, because of the cloud moving away, because of the repulsive forces of the electrons, created a slight positive and slight negative. So you have to have a contact area. So as they get closer, these forces increase. So that's a great way to show how when these two nonpolar molecules come in contact, their clouds actually shift and change shape, and this is called polarizability. And how well you can have polarizability determines the strength of these types of bonds. As I showed in class, so you can look, geckos actually stick, their feet will stick, or their hands both, will stick to surfaces and climb up almost anything by these London dispersion forces that occur with these tiny little hairs. Okay, so pretty interesting how animals use these forces to climb. All right, so polarizability with electrons. So we get back to our first example. As I said, chlorine and fluorine are gases. Their boiling points are obviously lower. They've boiled at below room temperature. That's why they're gases at room temperature. Bromide is a liquid and iodine is a solid, having a higher boiling point. Well, why does iodine have a higher boiling point than bromide? Well, because iodine is more polarizable. Its cloud is able to move more because it's got more electrons. So as you increase the number of electrons, you increase the strength of your LDFs, your London dispersion forces. And because iodine has more electrons than fluorine, chlorine, and bromide, it's actually a solid. Now, these are still temporary dipoles, and they're not very strong, and that's why iodine, even though it's a solid, sublimes at room temperature. It's a covalent compound, it's molecular, it's still got a low melting point compared to other solids. All right, and that's very important. So iodine is more polarizable. Its shape can change more. Remember, when these come together, these shapes change. And these electrons repelled these, and this positive nucleus attracted this side and pushed it over. And again, having more electrons creates a bigger negative, bigger positive, and these stick together, but only when they're in close contact, because when this moves away, okay, it doesn't attract anymore, and these dipoles go back to their original positions. That's why these are overall weak forces. Okay, which of the following noble gases has the highest boiling point? Well, neon or xenon? Well, if you look at the periodic table, xenon is atomic number 54 and neon is atomic number 10. Clearly, xenon has more electrons, therefore more polarizable, and because there's more movement in their shape, there's stronger negatives and positives created. Therefore, the attractions are greater between them, and xenon has a higher boiling point. Okay. Shape is very important as well. If you look at the shape of molecules, the longer chain hydrocarbons are generally nonpolar in real chemistry because the carbon to hydrogen bond is essentially nonpolar. So the longer the chain of alkanes, the stronger the bonds because you're adding more electrons with more carbons. But more importantly, a straight chain hydrocarbon is more polarizable than a smaller one, right? The more electrons are important, but as you get longer, you have more possibility of this cloud moving. So that's why the boiling points increase as the number of carbons are added to a carbon chain. Case in point, pentane with 5 carbons, what's called pent, has a boiling point of 36. Decane, dec is a prefix for 10 carbons in the chain, is 174. In fact, if we continue on this trend, we can see that these hydrocarbons, as we add more carbons, the boiling points increases. And there's my decane. In fact, asphalt is C, I believe, 35H72, and that's a solid. You know, asphalt is really a straight chain hydrocarbon, okay, or something close to that. And it's a solid at room temperature, but you still know it has what? Weak attractive forces. Remember, these LDFs aren't that strong. They become significant to make solids, but even those solids are not really that strong. On a hot day, we all know that asphalt gets soft and gooey because, again, their attractions aren't quite that strong. Significant enough, yes, to become a solid, but not significant to have a really high melting point. And asphalt on a hot day can be, you can remove it. If you notice how it's done, it's heated very hot and put down. Okay, so now we're going to look at some other shapes. Here I have pentane, okay, with my 5, and now I have an isopentane. This also has 1, 2, 3, 4, 5 carbons, but it's got a different structure. It's called a structural isomer that we'll talk about in organic chemistry. But in this case, this structure, being that it is in a more circular pattern, is not as polarizable as this structure here. So the boiling point of pentane being longer, even though these have the exact same number of carbon and hydrogen and the exact same number of electrons, the boiling point is much higher for the pentane because the electrons are able to move more. Because of the shape, it's more polarizable. In a circular shape, you can't create those dipoles because of the circular. It still creates some, but not as well. It kind of makes sense. You have to be longer to create the poles. Circle, it's harder to create those poles, those momentary poles. So shape is important. So everything's the same here. Number of electrons is the same, but being branched lowers, okay, my boiling point because it lowers my attractive forces because electrons are not as polarizable. Here's another example. These are all isomers. Now, if you notice, these things look like little lines here. These are carbon atoms bonded to carbon atoms. They leave out the H's, and you're just seeing the carbon chain. These are all structural isomers as well. And notice the boiling point drops as it branches. So as there's more branching, as it gets more what? Circular, okay, it becomes what? Less polarizable. It's a word you have to use. The straight chain is more polarizable, therefore the LDFs are stronger with a higher boiling point. So LDFs increase in size when the molecules are more polarizable. Now you can really, polarizable means they have more electrons or they have a shape that is more polarizable than if when the electrons are similar, are closer in distance and have pi bonding. Pi bonding occurs if you've got just have more electrons, okay, outside the plane. Okay, moving forward, don't forget that all molecules or atoms will have LDFs since they all have clouds of electrons. So as I said before, if I'm looking for an intermolecular attraction, no matter what, they all have LDFs. It all starts with a London dispersion force because they all have clouds of electrons. And you may say, well, give me an example, Mr. Grodsky. Well, I will. Think about CO2. We know CO2 is nonpolar because of the linear structure, and we know that water is definitely polar. How in the world does CO2 ever stay in water if they both have different attractive forces? And the answer to that question is, well, yeah, they do have different attractive forces, but they do have one in common, is LDFs. Yeah, water can induce a dipole on CO2. Its negative or positive side could cause the CO2's electrons to move to one side or another and create a LDF. It's not strong. That's why CO2 isn't that soluble in water, but there is some solubility. Just like O2, there's some O2 in water. Okay, because of the same reason, O2 is nonpolar. So the idea that like dissolves like definitely isn't exactly true. There are emulsion layers or some interactions, okay, between things that are polar and nonpolar, and those interactions are LDFs. Okay, moving forward. Now, the next attractive force is dipole forces or dipole-dipole. Dipolar forces are forces between things that are polar, and the things that are different about these is, unlike LDFs, these have permanent positive and negative sides, like water or hydrogen chloride, HCl. There's the positive, there's the negative. And of course, they stick together by the differences of the positives and negatives. Okay? And of course, the strength of these dipolar forces increase as these become more polar. The pair of electrons that is being shared unequally, let's say this is HCl, the more it is shared unequally, or as the electronegativity difference increases, the greater this negative and positive, and therefore the stronger that attractive forces. All right, but understand, just because I have dipolar forces, and this is due to nonpolar, don't forget that they also have okay, LDFs. So things that have dipolar forces have greater attractive forces because they have LDFs and they have dipole-dipole forces. Remember, this is a cumulative effect, all right? So just having dipole, they don't have dipole-dipole forces by themselves. They have dipole-dipole forces and they have the LDFs on top of them to increase the rate or increase the attractive forces. Okay, and here's some examples. We have 2-methylpropane, which is a branched hydrocarbon. It is nonpolar because of the carbon to hydrogen bonds clearly are just about nonpolar. That 0.4 difference, we consider them to be nonpolar bonds. So it doesn't matter. This whole thing just has LDFs. Now, 2-methylpropane and acetone have essentially the same number of carbons and hydrogens and electrons, and they have similar shape. So they have the same LDFs, London dispersion forces, almost exact same. But because of the polar nature of acetone, it has that plus. And because of the additional attraction on top of the LDF, acetone, my friends in chemistry, has stronger attractive forces. It's not just because they have dipole-dipole forces, they have dipole-dipole forces in addition to the LDFs. Notice the polar nature of sticking together. That's important. Look at methyl ethyl ether, and let's look at propanol. These have essentially the same number of carbons. I even know this is a carbon here, carbon, carbon, so 3 carbons, and the H's. This is showing the backbone. Okay? And they have the same shape. This is polar, this is polar. The boiling point is 8 degrees for the methyl ethyl ether, 97 for the propanol. What's the difference here? The difference, my friends in chemistry, is that they both have London dispersion forces, they both have a cloud, they both have dipolar forces, but one has an extra force, and that's called hydrogen bonding. So hydrogen bonding is a dipolar force. So essentially, the molecule that we just looked at, methyl ethyl ether, and we looked at propanol, these two only differ by one having hydrogen bonding. So this H to O scenario right here creates a extra molecular attraction that they have that this one doesn't have. And that's what adds to, of course, its higher boiling point. Now, the type of hydrogen bond is a type of dipolar force that is very, very strong. So, of course, having an additional bond and adding one that's very strong increases the boiling point significantly. Even though methyl ethyl ether and propanol have the same London dispersion forces and the same dipolar forces, this is the one that's adding to higher boiling points. It makes propanol highly resistive to evaporating. Now, what is H bonding? Why does this scenario here create such a strong extra attraction? Well, if we look at hydrogen bonding, it is a dipolar force, but it's one with the strongest type of polar attractions because we have a hydrogen hooked up with a very electronegative atom. And when hydrogen's hooked up with a nitrogen, oxygen, or fluorine, those are the 3 most electronegative atoms. And what they do is they create the most polar bond possible with the hydrogen. So pretend that this right here is a fluorine and this is a hydrogen. Fluorine being small and being highly electronegative pulls the pair of that pulls that electron so far away from the hydrogen that it's as if the hydrogen does not have the electron anymore, and all we have is this exposed proton. So let me talk about that once more. So if we had HF, okay, it would look something like this. We would have the fluorine. Oops, maybe not like quite like that. Looks like a brain. Okay, we take the fluorine, and then we'd have this little I don't know, bearing here. This would be the proton, and this would be the rest of the fluorine molecule, the rest of the fluorine atom. And that pair of electrons between the HF is shared very unequally, so much so that that pair is pretty close. Here, fluorine has 1, 2, 3, 4, 5, 6, 7. Hydrogen brings 1 to the table, but that pair is being shared unequally because of fluorine's great electronegativity difference compared to hydrogen. So because that pair is essentially almost pulled away, as we know, hydrogen has a mass of 1, its most common isotope, a atomic number of 1, so it has 1 proton, it has 1 electron when it's a neutral atom, and 1 minus 1, it's got 0 neutrons. So if this 1 electron is being pulled away to the fluorine side, then essentially you are just left with a proton. So we call these electron, this is a very important piece of vocabulary, deficient, okay, hydrogens. So when these hydrogens are electron deficient, and they only become electron deficient enough to cause hydrogen bonding when this H is hooked up with an F, or it's bonded with an O, or it's bonded with a nitrogen, NOF, or FON. Sometimes people will write that down. These guys are the most electronegative atoms, and they're also small enough to expose, okay, this proton at the end of the molecule. And having a proton at the end exposed, electron deficient, means that we almost have a +1 charge. See, when we write these partial charges of a molecule, right? Here's HF, and here's another partial charge. That would be the negative. This would be the positive side of the bond. So when you see these partial charges, it's because there's unequal distribution. There's not a transfer. Like an ionic compound, you'd see the full positive and negative. Okay, like sodium chloride, because of the transfer of electrons in this ionic scenario, you have brackets and charges. Here we have partial because there's not a complete transfer, although it is pretty close. So the point I'm trying to make here is that because the electronegativity difference of fluorine and oxygen and nitrogen are so high and they share so unequally, okay, they almost make this exposed electron deficient hydrogen almost +1. On top of that, what's the size of a proton? The size of a proton is very small, which means the charge density, okay, is very high. A lot of charge for a small spot. So this is highly attractive to other things that are negative. So an HF molecule, okay, will highly attract another, okay, HF molecule by these very polar or very dipolish E type of attractive forces, which are called H bonding. So this is really positive because essentially it's a proton with a small charge density. +1 is only in a small part of it, and it's really going to attract the negative part of the HF molecule very strongly. And that is the most strongest intermolecular attraction we have outside of ionic attractions, ion-ion. Some people consider ionic bonding not a bond, just an attractive force. So if we're talking about covalent types of attractions, H bonding is it. But you have to be aware it only occurs in these scenarios. You may say to Mr. Gronsky, if I look at the electronegativity of chlorine, that's very comparable to nitrogen, almost the same. Yes, it is. But hydrochloric acid, for the same reasoning, makes a polar compound, okay, and it definitely pulls that pair of electrons close to it. But because chlorine is a group 3, N=3 atom, its size, okay, of the atom is bigger than that of chlorine. Now you're still going to share electrons, but because of the size, it kind of limits the positive effect of the exposed proton. See, because the size of the chlorine is so big, it doesn't allow that electron deficient H to be exposed to attract to things as much as a smaller HF. Okay, right here that it can attract in all directions. So the size of the chlorine limits that, and that's why hydrochloric acid does not H bond. It only has dipolar, and of course it has London dispersion forces. HCl does not stick together by H bonds, only dipolar forces, and that's why hydrochloric acid, if you didn't already know, is a gas, okay? Gas dissolved in water. It is not a liquid, Okay, and you should see proof of that is when I have a bottle of concentrated hydrochloric acid. When I open it, you'll see the fumes come out, and that's a classic demo I showed you with Graham's law of effusion or diffusion when I put hydrochloric acid and ammonia next to each other. Okay, that gives you a better feel for why we're looking for electron deficient hydrogens in H bonding, why it's stronger, and why these are the only three elements with hydrogen that create that scenario. So back to propanol. Propanol is going to attract each other. The negative part of the oxygen will be attracted to the H of another propanol that's right here. Now, don't think that the rest of these H's can H bond as well. These are not electron deficient H's. They're hooked up essentially with a non-polar bond with the carbon here. So these are not electron deficient. So it'd be this one is the exposed proton that's positive that can attract the other negative of another propanol very strongly. Okay, so we're looking for electron deficient, and here's some examples. Okay, hydrogen fluoride, you can see salicylic acid, the H to the O, formic acid attracting itself, ammonia and water. Okay, reason why they're miscible and they can dissolve in each other. The negative part of the water attracts the positive, exposed proton of the ammonia, and likewise, glycine sticks together. HCl does not have hydrogen bonding, and that's the example I showed here. Okay, and see if I can see it here. Putting these two together, you can see the smoke that arises from HCl. It's a gas. All right, so this is the HCl molecules, and you can see when I open it up, the white smoke, of course, is the ammonium ion with the ammonium chloride, but the gas coming out of the hydrochloric acid results because this is not hydrogen bonding. This is dipole-dipole forces. It's not as strong because chlorine, although very electronegative, is too big and kind of engulfs the proton, so to speak, and doesn't make it as electron deficient as we would expect. Okay? So H bonding in water, of course, is the reason why water resists evaporation. When we looked at the 3 or 4 liquids, when we went back in time here, when we looked at these things, okay, here they are. Oops. Water is way over here. Well, why? Well, water has H bonding. Okay, it resists evaporation than the other 3. Now, of course, ethanol does too, and ethanoic acid. Propanol does not. Okay, but certainly water has strong H bonding effects, and that's why it resists evaporation, and that's why it was the liquid off to the side. The ones that acetone did not have, of course, evaporated faster. So the strength of intermolecular attractions resulted because of that H bonding. Okay, so and here we have water. It's a nice little animation. It shows how many different attractions stop and start as water is dissolving with solute particles. You can look at that on your own. Interesting to see how many different attractions occur on and off as water moves into each other, and shows how water is, of course, more dense as a liquid and less dense when it finds a very stable state as its structure of its crystalline ice structure. Okay. Any case, to look at the differences of bonds and intermolecular attractions, we're going to start doing that. An average carbon-to-carbon bond, the strength of that bond energy is 345 kilojoules per mole. Dispersion forces in propane is about 0.1 to 5 kilojoules per mole, so very, very weak. Dipolar forces, now we know in dispersion forces or London dispersion or LDFs, they can become more significant as you become more polarizable with more electrons or the distance increases. Dipolar forces like an acetone or propanol is 5 to 20 and H bonding is 5 to 50. So you can see that the strength of intermolecular attractions increase as we go from the LDFs to dipolar to, of course, hydrogen bonding, but nowhere near the strength of the bonds between the atoms. Okay, it's very important. And of course, if you remember making slime, if you have never done that, of course, we do that because we just like to. What links the polyvinyl alcohol chains, that sodium tetraborate, okay, ion, is the H bonding of this borate ion. So the solid lines indicate the molecule, and the dotted lines represent the attraction. So right here represents one polyvinyl alcohol polymer being linked to the borate, which is linking to another by, guess what, H bonding. And you felt that. If you make slime and it was stirring it, it got firmer. That H bondings, of course, were increasing. You should know, of course, this is DNA. And DNA, okay, or basically a holder of our genetic material, is held together by H bonds. And there we go. H bonds right here that link the adenine and the bases that we've talked about. All right. Kevlar. It's a polymer that stops bullets, but what's stopping bullet is the H bonding between, look at this, the H and the O. Okay, the H, the N here is creating electron deficient enough proton exposed to attract the negative part of the O. Okay, but H bonding stopping bullets. Okay, strength of dipolar force, or H bond, since it is a type of dipolar force, is based on the degree of polarity of the bond. Okay, and of course, if you look at, this is a very famous chart that you'll see all the time, look at some trends here. Now, if you didn't already notice, tellurium, selenium, and sulfur going up group 16. Notice the boiling points, in case from sulfur to selenium to tellurium, they increase as we go from period 3 to 4 to 5. And that's because we're adding more electrons, and that's because the London dispersion forces are increasing. So you'd expect oxygen to be lower because, well, oxygen has less electrons than sulfur, selenium, or tellurium. These are the same structures, H2SE, H2TE, H2S, and H2O would expect to be lower in group 2 because oxygen has less electrons, less polarizable. The London dispersion forces, those momentary charges, should be less, but in fact, they're not. What makes this leap off the chart is because H2O has what? Has H bonding that H2S and the rest of these don't. So you see the ones that break the trend are the what? The O, the F, and the N. These are the ones that have the H bonding. And because H bonding is a significantly higher attractive force, the boiling point is greater. Okay, so this is almost in every textbook. And this is a very important one. So let's look at some solids, some types. We have molecular compound. This is a fancy word for covalently bonded because they make molecules, a definite finite number of atoms bonded to each other as act as a particle. And if you notice, dispersion forces are low. Example is argon, melting point 84 Kelvin. Okay, dispersion. Then we have dispersion and dipolar. Okay, so which means now we have dipolar forces. This means if you are polar, you also have dispersion, but now you're adding dipolar. Your energy now goes from 5 to 25. Okay, and then of course HCl is an example. It doesn't H bond. Its melting point is 158 Kelvin, which is lower than 273. That's why it's a gas. Then we have H bonding, but you notice that this, they put dispersion, dipolar, and H bonding because you can't be one without the other. If you have H bonding, well, you're still polar, and you have also a cloud of electrons, so you have LDFs. And this is 10 to 40. Water is an example, and look at 273. So the boiling points increase as you add the other attractive force. And as I talked about before, it's not just one or the other. It's a cumulative effect of all of them. Metallic bondings. These are called delocalized bonding. We've talked about that. But they have much stronger energies. These are actually bonds, so they're actually much greater in force than any of the attractive forces. Copper is an example. Its melting point is very high. The sea of mobile electrons. We'll talk more about that in another lecture. Network bonds or network solids. These are a network of covalent bonds. Silicon dioxide, diamond. Okay, these guys have crystals in the covalent compound. Molecular compounds generally don't make crystals. The ones that do are network solids. And there's only 3. Silicon dioxide, silicon carbon, and diamond. These are nonmetals or semimetals that bond covalently in all directions. And they have very high melting points because of their crystalline structure with the covalent bonds. And of course, ionic have very high melting points because positive and negative is a very strong attraction. And an ionic compound, all right, this attractive forces are electrical. These are Coulombic attractions. And these are positives and negatives. They're going to be much, much stronger than anything that the attractive forces can be that are partial charges. Okay, H bonds try to get there, but nothing's going to be as great as the ionic. Okay, and then we have ionic force, cation to anion. Okay, huge energy to break these. We talked about lattice energy. Covalent, the bonds are going to be weaker. Okay, you're sharing, nuclei are fighting over electrons. Here you have Coulombic attractions of positive negatives, always going to be greater. And metallic, okay, are going to be also high in energy to break because the sea of mobile electrons that all the nuclei can imagine. And of course, the delocalization of electrons here adds to the stability. All right. And then here we go with some other ways to look at it. Ion dipole. We call these molecule ion attractions last year. These are the famous boyfriend, famous girlfriend. And these are significant, especially as we talk about solutions. H bonding. Okay, and you can look at the energy. So associated with these attractive forces, dipole-dipole. Ion-induced dipole is a scenario where you take something that an ion will cause something nonpolar to be polar by repelling or attracting electrons. And dipole-induced, same idea. Something nonpolar is induced. Notice these dotted lines show the squishiness, as the video would say, or the polarization of nonpolar molecules. You can force them to be somewhat polarized by either an ion or a polar molecule. And of course, you notice the ion dipole is a little stronger because this is a permanent, full positive or full negative. These dipole-induced, although permanent dipoles, they're not a complete positive or negative. And of course, the dispersion forces are the weakest forces. All right. So with that, I should be able to continue on with the worksheet and see how you do with that.